now we'll start with the second part of the video and we'll do some questions regarding the Nernst equation and finding the E cell of the reaction potential, electrode potential for the reaction and electrochemical cell. And also we'll study the conductance, the Coriolis law, Faraday's laws, etc. in the further part of the video. So starting with the Nernst equation. Nernst studied the variation in the electrode potential of an electrode with the temperature and concentration of the electrolyte. So basically he formulated this equation between the standard electrode potential, that is E naught, this is the standard electrode potential, and the electrode potential of the cell. So as per this following equation, the electrode potential of a cell varies with the temperature and concentration of electrolyte. So the actual form of the equation is E is equal to E naught minus RT by NF ln Q, or ln K, we can consider it as K. It is the basically the product of product concentration raised to power the stoichiometry divided by the reactant concentration raised to power the stoichiometry, let's say Q something, stoichiometry. So if we convert this ln into log, then we'll multiply with 2.303. So E is equal to E naught minus 2.303 RT by NF log Q. Okay. So let's say writing a simple equation, Mn plus ions taking n electrons are converting into M solid. So if we are going to write the Q for this is M solid divided by concentration of Mn plus ions. So since the stoichiometry over here is 1, so it is it raised to power 1. For solid the concentration is taken as 1. Therefore we are will only get the Q as 1 by a concentration of M ions with N positive charge. So that's why it is written like this, because the product over here is solid whose concentration will be taken as 1. Okay. So at 2, and also this factor, that is 2.303 RT by NF, where R is gas constant, T is temperature, F is Faraday's constant. So if we put all the values at 298 Kelvin at room temperature, the value will come out to be 0.0591, actually 591. So that's why it has been simplified by writing 0.0591 at 298 Kelvin. Okay. So Nernst equation, when applied to a cell, it helps in calculating the cell potential, that is E cell is equal to E naught minus 2.303 RT by NF log anode ion or cathode ion. We can say anode ions because metal, let's say metal at anode will in the solid form will ionize into Mn plus ion plus N electrons. Similarly, cathode ions, let's say N is the cathode ion. By taking N plus electrons, it will convert into N solid. So for the overall reaction, M anode plus N plus ions cathode will give you Mn plus ions plus N solid. So basically if you write the Q for the reaction, that is product concentration over reactant concentration. So the product we are having Mn plus ions, which are the ions coming from the anode. Okay, that's why it is written as anode ion. And if you consider the reactant over here, we have N plus ions. The rest part, that is N solid concentration, it will be taken as 1 because they are in solid state. M anode, in solid state concentration will be taken as 1 there, that's why it is written in this form. So it could be simplified as this. At equilibrium, the E cell, this E cell becomes 0, and the solution and the equation becomes E cell is equal to 2.303 RT by NF log this concentration. Okay. So at equilibrium, the relationship becomes this, and the this Q, or we can say the this factor Q or Kc, it becomes equilibrium constant. It is now become a constant, equilibrium constant. Okay. So from this equilibrium constant, you can calculate the delta G naught, that is the Gibbs free energy. So delta G naught is basically minus NF E naught cell. So if you know the value of E naught cell, that is this one, you can substitute it over here, and you can get delta G naught is equal to minus NF E naught cell is equal to 0.0591 by N, and say N to N will get cancelled, log Kc. So this will be your equation. Now we'll do some questions with using the Nernst equation. Please calculate the value of the equilibrium constant for the reaction at 298 Kelvin, where the copper solid is converting into copper 2 plus ions, and the two silver ions are converting into two silver solid. So given are the values of the E naught for the reduction of silver ions and E naught value for the reduction of copper ions. Please try to solve the equation. Please try to solve the question. In this question, we are provided, as we know that equilibrium constant they have asked us. So what is the Nernst equation? E cell is equal to E naught minus 2.303 RT by NF log K. Okay. So at equilibrium, busy E cell is equal to 0. So we have at equilibrium we have E cell is equal to 0. So therefore the equation term becomes 0 equal to E naught minus 2.303 RT by NF log. Now this constant becomes equilibrium constant. Okay. So simplifying the equation, we have E naught is equal to 2.303 RT by NF log Kc. Okay. So So, modifying the equation further, we need to calculate the log Kc. So, multiplying NF over here, NF E naught divided by 2.303 RT equal to log Kc. This is the formula that we will be using. So, first we need to calculate E naught. E naught cell is equal to E cathode minus E anode, E naught cathode minus E naught anode. So for E cathode, what we have? E cathode, which one is acting as cathode over here? The silver ions has a potential of 0.80 and the copper 2 reduction ions have 0.34. Therefore, the higher the potential, more is the tendency to get reduced. So, copper ions are the silver ions will get reduced. So, the 0.80 minus 0.34 will get E naught cell as 0.46 volts. Okay. Now substituting the value in this equation that we have modified, equilibrium constant is equal to 2 because we have the N over here is 2. The copper 2 plus ions will take 2 electrons to convert into copper 2. Therefore, we are taking N is equal to 2. 2 into F, that is 96500 Faraday's constant, multiplied by E naught, that is 0.46, divided by 2.303 into 8.314 into temperature, that is 298 Kelvin. So we'll be getting a value of 15.59 log Kc. Now in order to find Kc, we need to take the anti-log of this. Anti-log for this will give you the value 3.92 into 10 raised to power 50. So this is the equilibrium constant for the following reaction. Okay, please check the values and your answer match your answer. Okay, we'll move to the next question. The cell in which the following reaction occurs has an E naught cell of 0.236 volt at 298 Kelvin. Calculate the standard Gibbs energy and the equilibrium constant for the reaction. Please try to solve this question by yourself. I'll do it in 1 minute. So for this reaction, we have 2Fe3 plus ion are convert and along with the 2I minus are converting into 2Fe2 plus I2. So here you can see iron 3 is going into iron 2. A change in oxidation state of 1. But you can see 2 is the stoichiometry over here. So we can say 2 electrons are being consumed. Similarly, one I molecule is converting into I. So 2 I minus molecules are releasing 2 electrons to form I2 gas, I2 solid. So we here 2 electrons are being consumed. So we can say that N for the reaction is 2. Okay. Now, in order to calculate Gibbs free energy, that is delta G naught is equal to minus NF E naught cell. Okay. E naught cell they have provided that the E naught cell value is this. So we can say that delta G naught, substituting a value of 2, that is N, that is 2, 96500 for Faraday's constant, and E naught value, that is 0.236. Now please calculate the value. The value will come out to be minus 45548 joules delta G naught. Coming to the calculation of equilibrium constant, we know that E naught cell is equal to 0.0591 by N log Kc. Now multiplying it in that we will be having N E naught cell divided by 0.059 is equal to log Kc. Therefore, substituting the values, 2 into 0.236 divided by 0.059 will be having log Kc. Now taking the anti-log, will be having this value will give you 8. So anti-log of 8 will give you 10 raised to power 8. The Kc value is, equilibrium constant is 10 raised to power 8. This is the answer. Coming to the next question. What is the cell potential of the reaction at 298 Kelvin where two aluminium molecules are converting into two aluminium 3 plus ions and 3 copper 2 plus ions are converting into 3 copper solid molecules. So, given that E naught cell for the reaction is this, aluminium ion concentration is this, and copper ion concentration is this. Please try to calculate the value for the cell potential, that is E cell you need to calculate. Try to use the Nernst equation. So, writing the Nernst equation first, E cell is equal to E naught cell minus 0.0591 by n log. Here we'll be writing in the form of like this, product concentration divided by the reactant concentration. Okay, so here product concentration raised to power the stoichiometry, so n or q, something like that. So E naught cell they have already provided 2.00 volt minus 0.0591. What is the value of n over here? Copper 2 plus is converting into copper solid. So it is basically using uh, 2 electrons for the conversion. Copper 2 plus require 2 electrons to convert into copper solid. But 3 molecules of copper 2 plus will be requiring 3 into 2, 6 electrons. So the n value over here is 6 log. Product concentration will consider aluminium 3 plus raised to power 2 by divided by copper 2 plus raised to power 3. So substituting the value of aluminium 3 plus ion, that is 0.1, and substituting value of copper 2 plus, that is 2.5. So we'll solve this equation. 0.1 square divided by 2.5 cube, 0.0591 by 6 minus 2. So upon solving the equation, this value will give you log of 6.4 into 10 raised to power minus 4, that is 0.0591 divided by 6. Therefore, here we'll be having the E cell value of E cell is equal to E naught cell minus 0.0591 by 6 log of what? 6.4 into 10 raised to the power minus 4. Upon solving this equation, you will be getting E cell as 2 minus 0.0591 by 2 log of this value. The E cell will come out to be 2.03 volts. Okay. Moving to the next question. What is the cell potential of the electrochemical cell in which the cell reaction is lead 2 plus combining with the cadmium will change into lead plus cadmium 2 plus ion? Provided that the E naught cell for the reaction is 0.277 volts, temperature is 225 degrees Celsius, that is 298 Kelvin, and concentration of these ions. So as we know that E cell is equal to E naught cell minus 0.0591 by log of what will we be writing, cadmium 2 plus divided by the lead 2 plus. So substituting the values 0.277 minus 0.0591 by log, how many electrons are being consumed? 2 over here, 2 over here, and cadmium is also uh, taking 2, releasing 2 electrons. So N value is 2, log cadmium concentration is 0.02, lead concentration is 0.2. So solving the following equation, we will be getting log of 0.1, 0.277 minus 0.0591 by 2, or we can write 0.277 minus 0.0296. Log of 0.1 will be minus 1. So we'll be having value 0.277 plus 0.0296. Adding the two, we'll be getting E cell as 0.277 plus 0.0296. The value is 0.3066 volts. This is the answer. Coming to the next question. The copper 2 plus ion concentration in copper silver electrochemical cell is 0.1 molar. If E naught for the silver ion reduction to silver is 0.8 volt and copper 2 plus ion reduction to copper is 0.34 volt, cell potential at 298 Kelvin or 25 degrees Celsius is 0.422 volt. Find the concentration of silver ions. So here again, try to use the Nernst equation, that is E cell is equal to E naught cell minus 0.059 volt by N log here silver ions are getting reduced to silver and copper is getting oxidized to copper 2 plus. 2 electrons are released over here, 1 electron is consumed over here, so it will be multiplied by 2. So overall reaction is 2 silver 2 plus ions plus copper is converting into silver 2 silver molecules plus 1 copper 2 plus ion. So E naught cell first we need to calculate. E naught cell will be E cathode minus E anode. What is the cathode over here? Cathode is silver. 0.8 minus anode is 0.34, that is copper 1. So the value will come out to be 0.46 volts. So substituting the value of E naught cell, that is 0.46 minus 0.0591, N value we know 2 electrons are being consumed or taken, so N value is 2, log of, now as per the final equation we have in the product copper 2 plus ion and in the reactant we have silver ion raised to power 2. So the concentration of copper 2 plus ion in the given electrochemical cell is 0.1. They have mentioned that the concentration of copper 1 is 0.1. Silver they have asked us to calculate. So we need to calculate the silver ion concentration. For this reaction they have mentioned that the cell potential is 0.422. So 0.422 they have provided this number, 0.46 is the uh, E naught value. So we will calculate the value of silver ion. So rearranging the whole equation, we will be getting 0.1. First, will 0.422 minus 0.46 negative 0.0591 by 2. Here we'll try to solve the log first. So we have log of zero point 0.1 is minus 1 minus 2 log of silver ions. Okay. So this is in the multiplication. Therefore, in total we'll be getting the value, that is 2 log silver ion minus 2 log of silver ions will give you, trying to rearrange the whole equation, will be getting 1.283 plus 1 will give us 2.283 minus 2 log of silver ion. So dividing it by 2 will be getting log of silver ion as minus 1.141. So silver ion concentration will be anti-log of this number, that is anti-log of minus 1.141. If you do the calculation by calculator, the value will come out to be 0.722 molar. Let me write over here 0.0722 molar. This is how you are supposed to solve these questions. Let us move to the next one. Calculate the EMF of the cell in which the following reaction takes place. This one is easy. Please try to calculate the value by yourself. I'll solve the equation in 2 minutes. So in the following reaction, again you are supposed to use the Nernst equation. So for the Nernst equation, what we have E naught E cell is equal to E naught cell minus 0.0591 by n log of, they have provided the equation, so it will be easy to write for you this time. Nickel 2 plus iron divided by silver ions raised to power 2. So substituting the values over here, nickel 2 plus is 0.002 and silver is 0.160. So again rewriting the equation, E cell is equal to E naught cell. The how many electrons are used? Silver ion is converting into silver. So 1 electron for that into 2 for stoichiometry. Overall 2 electrons are being consumed. So minus 0.0591 divided by 2 log of nickel 0.002 concentration they have provided. For silver they have provided 1.16 raised to power 2. Okay. So what is the E naught cell value they have provided? They have provided E naught cell is equal to 1.05 volts minus 0.0591 by 2 log of, solving this equation you will be getting, okay, I wrote it wrong. It is for nickel it is 0.160 and for silver it is 0.002. So it is 0.16 0.002 square. Solving this equation you will be getting 0.16 divided by 0.002 square. You can solve it by using a calculator. E cell will give you uh, 1.05 minus 0.0591 by 2 log of 0.16 by 0.002 square. So you will be getting the finally the answer will be 0.914, sorry, 0.914. E cell is equal to 0.914 volts. So I hope you guys understood. We'll move to the next topic, that is conductance in the second part. Yeah, further, we have solved 4-5 questions for the finding using the Nernst equation, where we try to calculate the E cell for the reaction, E naught cell, and the equilibrium constant and the Gibbs free energy. Now we'll move forward to the conductance. For the conductance, as we know, the substance that allows the passage of electricity through them are known as conductors. Okay, so electricity is basically the flow of electrons. Okay, so every conducting material offers some obstruction to the following of electricity. See, if electrons are being moving, so there will be some resistance to that. In metal, there are a positive charge in the form of kernels, and electrons are present. Basically, there is a sea of electrons, and the positive charge is present in the form of these kernels. So the electrons are moving, and they are being resisted by the their movement is being resisted, and that resistance is called the or we can say the obstruction is called resistance. Okay, so how resistance is calculated in the physics, you have all already studied that how resistance are calculated. Resistance in any object depends upon the length and area of the object through which the electrons are following. So resistance is basically directly proportional to the length and is inversely proportional to the area. So we can say that resistance is equal to, removing this proportionality sign, uh, putting a constant L over A, that is, this constant is called resistivity constant. Resistivity, this is the length of the material through which the electrons are flowing, and this is the area of the material, and the resistance is calculated in this fashion. Unit of resistance is ohm, OHM. Symbol is like this, and the length is centimeter. Area, it will be the centimeter square. So overall, we can say that resistance is equal to rho L over A, or ohm is equal to rho centimeter over centimeter square, or we can write from here the units for the resistivity constant, that is, you will cut centimeter with the square, so we'll be having ohm centimeter. So the units for the this resistivity are ohm centimeter. So resistance is rho L over A, where rho is called the specific resistance or resistivity. The unit the SI unit for the resistivity is ohm centimeter. In the SI, we can say it is meter. Length is in meter. Area is in meter square. So we'll be getting meter over there. So inverse of resistance is the conductance. Now, resistance is basically the obstruction in flow of electrons, while opposite of this resistance is conductance. So we can say resistance is equal to 1 by G, and G represents the conductance. So if we have the formula for resistivity as rho is equal to L over A, we can write resistance as 1 by G rho L over A, where rho is the resistivity, L over A is the cell constant. So writing it in another way, we can say resistance is equal to 1 by G, that is conductance, rho L over A. So this rho, just reversing the equation, we can say A over L, uh, and 1 by rho will give us G. So this 1 by rho, that is a reverse of resistivity, is called conductivity. Conductivity, which is represented by kappa. This kappa is the symbol for conductivity, and A over L is called cell constant, represented by capital K. So we'll be having the equation G is equal to kappa into capital K. Okay. Conductance is equal to conductivity constant into cell constant. Okay. Or the unit of conductance is ohm inverse. Since the unit of resistance, so we just derived that G is equal to kappa into capital K, and G is equal to 1 by R. So we can say if the unit is resistance is ohm, then the unit of G will be ohm inverse, or we can also call it as Simon. Okay. If the inverse of resistance is called conductivity, it's represented by small k, that is kappa. The SI unit of conductivity is Simon per meter. So how did they calculate this? As we know, resistance is equal to rho L over A. Resistance is equal to 1 by G rho L over A. Rearranging the equation, G A over L 1 by rho will give us G. G is ohm inverse. We just saw that it is the reverse of conductance, and conductance is this. 1 by rho, reverse of resistivity is conductivity kappa, and A over L. A is the area, meter square, length is the in meter, so meter will cancelled. So meter into conductivity will give us Simon inverse, or we can say this ohm inverse, or we can just call it as Simon, represented by S. So unit of this conductivity will be Simon divided by meter, or we can call it as Simon meter inverse. That's how they just calculated the units over here. Okay. So conductivity, we just saw that conductivity, if we write this equation in the form of conductivity, we can say conductivity is equal to conductance into L over A, that is cell constant, G into capital K. L over A. Sorry, it is not capital K, it is L over A. Okay. So we'll do some questions now based on this resistance formula and the conductance formula. So the first question says the resistance of a conductivity cell uh, containing 0.001 molar KCl solution at 298 Kelvin is 15,000 ohm. What is the cell constant if the conductivity of the 0.001 molar KCl solution at 298 Kelvin is this much? So please try to use the formula that we discussed in the previous slide. As we know that conductance is equal to, or we can say the conductance is a reverse of resistance, and resistance is equal to rho L over A. So we can write, and this rho is reverse of conductivity. So it's rho conductance is equal to kappa A over L. Okay. So now you can say the resistance of the conductivity cell containing 0.001 molar KCl solution at resistance is equal to 15,000 ohm. What is the cell constant? They want us to calculate the value of the cell constant, that is L over A. So L over A will be equal to kappa divided by G. Kappa is conductivity. They have mentioned the conductivity, the resistance of a conductivity cell containing this solution. Resistance they have mentioned. So you will write resistance as reverse of conductance. So you will multiply it with 15,000 ohm. You can write G as R into R. Okay. So we'll be writing 1500 ohm over here. Conductivity they have mentioned as 0.146 into 10 raised to power minus 3 Simon centimeter inverse into 1500 ohm. We know that Simon is equal to ohm inverse. So this unit and this unit will be getting cancelled. We will be having 0.146 into 10 raised to power minus 3 into 1500 centimeter. So solving this equation will get L over A, which is cell constant. L over A. After solving this, we'll get 0.219 centimeter inverse. We'll do one more question. Okay, we'll do that later. So, um, for measuring the resistance of the ionic solution, there are basically two problems. The two problems are: firstly, passing direct current changes the composition of the solution, and the second problem is a solution cannot be connected to the bridge like metallic wire or a solid conductor. So these are the two problems. Now we are moving to the conductivity cell. The conductivity cell, basically the cell where we are measuring the conductivity, it has specific dimensions, and the problems of measuring the resistance can be resolved. We discuss these two problems. No, the first, passing the direct current change the composition. Second, cannot a solution cannot be connected to the bridge like a metallic wire or a solid conductor. Therefore, in a conductivity cell, these problems are solved for measuring the resistance by using the source of alternating current. Direct current we are not passing, we are passing alternating current. And the second problem is resolved by using special design vessel called conductivity cell. A conductivity cell has specific dimensions. The length with a specific length and the area of the electrodes are defined. So a conductivity cell consists of two platinum electrodes coated with platinum black, having a cross-sectional area A. They are separated by a distance L. So basically, in a conductivity cell, uh, there are two electrodes, and the distance between those electrodes are defined, that is L, and the resistance of the column is given by the equation resistance is equal to rho L over A, where rho could also be written as 1 by kappa, that is conductivity L over A. One L over A is called the cell constant, and it is denoted by this symbol J star, or you can also write it as capital K. There are different notations people use. So some people write it as capital K, or someone could write it as G star. So molar conductivity. Now we just defined that conductivity cell has a length of 1 centimeter between the platinum electrodes. Uh, so molar conductivity for such solution could be defined as the conducting power of all the ions produced by dissolving 1 mole of electrolyte in the solution, provided the length is 1 centimeter and area of the electrode is 1 meter square. So basically the length over here is 1 centimeter. So, and the area of area in which the electrodes are immersed, so that is also 1 centimeter square. So molar conductivity is defined by this symbol called lambda. Lambda is equal to 1000 into kappa, that is conductivity, divided by the molar conductance, divided by the molarity, sorry. So where kappa is the conductivity and m is the molarity unit of the molar conductivity. Units for the molarity will come out to be Simon centimeter square mole inverse. We'll do one more question for this. Conductivity for the 0.01 molar NaCl solution is this. Calculate the molar conductivity. We just saw that molar conductivity is equal to kappa into 1000 by m. So just substitute the values that molar conductivity of a 0.01 solution. Molarity is 0.01 molar. Kappa they have mentioned conductivity of the solution is 0. Conductivity of the solution they just mentioned 0.12 Siemens meter inverse, and they have written as per the equation it is 1000. So calculate the molar conductivity over here. The value will be 1.2 into 10 raised to power minus 2 sine. Okay, sorry. The value will be 1.2 into 10 raised to power minus 2 Siemens centimeter square per meter square. Coming to the next question, the molar conductivity of 0.1 molar nitric acid is 630 Siemens centimeter square per mole. Calculate the conductivity. Here you can say molar conductance is equal to kappa into 1000 over C. The molar conductivity of nitric acid they have mentioned 630 Siemens centimeter square per mole into 1000, and with conductance you have 0.1 mole. Molar you can write moles per liter. So you will be having this per mole and this mole will get cancelled, and the kappa they have mentioned the molar conductance they have mentioned. This is the molar conductance, and you need to calculate the conductivity. This is not basically kappa you need to calculate, and this is the molar conductance they have mentioned 630 Siemens centimeter square per mole. So kappa will be 630 Siemens centimeter square per mole into 0.1 mole per liter divided by 1000. This mole and this mole will cancel out, and you will be left with the value, that is kappa is equal to 630 into 0.1 divided by 1000, giving a value of 0.063 Siemens centimeter inverse. Moving to the next question, the electrical resistance of a column of 0.05 molar NaOH solution of diameter 1 centimeter, length 50 centimeter is this much. Calculate the resistivity, conductivity, and molar conductivity. Please do the question by yourself. I'll do it in 1 minute. As they have mentioned that cell constant or G star is equal to L over A. So length is 50 centimeter they have mentioned, and radius is and since they have mentioned a column they have mentioned, so Diameter is 1 centimeter, radius will be 0.5 centimeter. So area for the this will be pi r square. Pi r square, that is 3.144 pi and 0.5 square. So you will be getting the area as 0.785 centimeter square. Substituting the value over here, 0.785 centimeter square. So G star will come out to be uh, 63.694 centimeter inverse. This is the cell constant for the reaction. Now finding out the resistivity. Resistivity. So resistance is equal to rho L over A. We need to calculate this rho. And we have already calculated the G star, that is cell constant. Resistance, they have mentioned electrical resistance is 5.55 into 10 raised to power 3 ohm. We need to calculate the resistance, and resistivity we have already calculated. The cell constant we have already calculated, 6.94 centimeter inverse. So resistivity will be 5.55 into 10 raised to power 3 divided by 63.694 centimeter inverse. So we'll be getting a value of the value will be close to like 87.135 ohm. Now coming to the conductivity. Here's my icon. Okay. Conductivity, that is rho. Resistivity, conductivity, that is kappa. Kappa and resistivity are inverse of each other. So we can just write that resistivity inverse is equal to kappa. Conductivity will be 1 by 87.135 ohm, or we can say it is 1.148 into 10 raised to power minus 2 ohm inverse. Third, we need to calculate the molar conductivity. Molar conductivity, that is lambda m, is equal to kappa into 1000 divided by the concentration. So we have 1000 into kappa, we have already calculated 1.148 into 10 raised to power minus 2 ohm inverse. Concentration they have mentioned, that is 0.05 molar. So solving the following equation, will be getting 229.67 centimeters square per mole. So this is the value for molar conductivity. Okay, that's how you are supposed to solve the equations. Now we'll discuss the equivalent conductivity. Equivalent conductivity is the conductivity of the ions produced by dissolving 1 gram equivalent of the electrolyte in the solution. Unit of the equivalent conductivity is Simon centimeter square, or we can write this as gram equivalent, gram Simon centimeter square into gram equivalent inverse. So this is the formula for equivalent conductivity, where the lambda it is represented by lambda E, whereas molar conductivity was represented by lambda M. It could be written as conductivity into 1000 by normality. Okay, so moving to the next part, that is Coverlow's law. Coverlow's law of independent migrations of ions. So basically these law discuss that according to this law, molar conductivity of an electrolyte at infinite dilution can be expressed as a sum of individual contribution from its individual ions. See, if molar conductivity of a NaCl, you need to see, let's say NaCl. Okay, for NaCl at infinite dilution, that means it will be dissociated into sodium ions and chloride ions. So molar conductivity of NaCl, that is molar conductivity, lambda represents molar conductivity, infinite dilution we represent by this infinity sign, is equal to molar conductivity of sodium ions at infinite dilution plus molar conductivity of chloride ions at infinite dilution. So this law says that for an electrolyte, molar conductivity of an electrolyte at infinite dilution is equal to the sum of you know, it is a sum of the sodium plus ions and the sum of the molar conductivity at infinite dilution for the chloride ions. If the limiting molar conductivity of the cations is denoted by the lambda plus naught and that of the anions is denoted by lambda minus naught, then the limiting molar conductivity of the electrolyte will be this number. This is the stoichiometric number of the ions and the stoichiometric number of anions. For example, you are writing for the MgCl2. For this, you are getting two manganese ions and two chloride ions. So, for this, the molar conductivity of MgCl2 at infinite dilution will be the molar conductivity of Mg2 plus at infinite dilution plus 2 times the molar conductivity of chloride ions at infinite dilution. So, because two chloride ions is released, therefore we will multiply this. Okay. Now we'll do some questions. Calculate the molar conductivity of the solution of MgCl2 at infinite dilution, given that the molar ionic conductivities are these. This is a very simple question. Please try to do it by yourself. So, as we understood that MgCl2 on dilution will convert into Mg2 plus and 2Cl minus ions. So, at infinite dilution, we'll be having lambda MgCl2 at infinite dilution will give us lambda Mg2 plus at infinite dilution plus 2 times lambda Cl minus at infinite dilution. Now, substituting the values for manganese, it is 106.1 plus 2 times 76.3. So, solving this equation, you will get you will be getting 258.7 Simon centimeter square per mole. So, see how simple it is. You just need to add up the individual values. Okay, try to solve this one. This is also similar. So for this question, the value of the limiting molar conductivities of ammonium chloride, ammonium chloride will dissociate into ammonium plus chloride minus. NaOH will dissociate into sodium plus hydroxide ions, and NaCl will dissociate into sodium plus chloride ions. Okay, so they have mentioned the values over here. Calculate the limiting molar conductivity of ammonium hydroxide. So in order to make ammonium hydroxide, you need ammonium ions plus hydroxide ions. So you need to arrange these three in such a way that you will get the formation of ammonium hydroxide. Let's say uh, you are adding this two and subtracting this one. That means you are adding Na and NH4Cl plus sodium hydroxide minus NaCl. That will give you NH4 plus Cl minus uh, plus sodium ions plus OH minus minus NaC Na plus minus Cl minus. So this Cl will get cancelled, this Na will get cancelled, and you will be left with ammonium ions and OH minus ions. That will give you ammonium hydroxide. So we just added the above two and subtracted the NaCl. So lambda infinity value for this is ammonium chloride is 149.74 plus ammonium sodium hydroxide is 248.1 minus for NaCl is 126.4. You will get the value of ammonium hydroxide, that is 271.44 Simon centimeter square per mole. Okay. We'll discuss about degree of dissociation now. Degree of dissociation is defined as the ratio of molar conductivities at a specific concentration to the molar conductivity at infinite dilution. It is denoted by the symbol alpha. Degree of dissociation constant K alpha is equal to C into, basically, if you are seeing A is getting converted into B plus C. So, um, you need to degree of dissociation you need to calculate, then it will be like equilibrium constant. So concentration of B, concentration of C divided by concentration of A. Let's say you initially have 1 mole and this was 0 0. After some time it changed to, it dissociated by alpha amount, 1 minus alpha into alpha over alpha. So substituting the values, C alpha into C alpha divided by 1 minus alpha. So you will be getting C into 1 minus alpha. This C will cancel with this C. You will be left with C alpha square over 1 minus alpha. So that's how you calculate the degree of dissociation, where K alpha is the acid dissociation constant and C is the concentration of the electrolyte and alpha is the degree of ionization. Now coming to the electrolysis. Electrolysis is basically when you pass electricity in order to carry out a non-spontaneous reaction. So it is to understand electrolysis, first you need to understand the Faraday constant and the unit of uh, like how much energy electrons pass and how much electricity will be there. So if Faraday constant, first understand this term, it is equal to the charge of 1 mole of electrons. So 1 electron, the charge is 1.196 into 10 raised to power minus 19. Okay, for 6.022 into 10 raised to power 23 electrons, that is 1 mole of electrons. Multiply this with 1.196 into 10 raised to power minus 19. You will be left with 96500. This is the charge for 1 mole of electrons. Okay. Now this is defined as capital F Faraday. Now that we'll study about the electrolysis. Electrolysis we can understand by Faraday's law. Faraday gave first law of electrolysis where he said that the amount of substance deposited during the electrolysis is directly proportional to the quantity of electricity passed. So he said that the amount represented by W is directly proportional to the electricity passed, and when we remove this I, the proportionality sign, we can say I into uh, T, or we can say it is directly proportional to the charge, and charge is basically could be equal to the current passed for definite time interval. So the other law that that Faraday gave, he said the same charges is passed to the different electrolyte. The mass of the substance deposited will be proportional to the equivalent weight. For example, if you are passing 1 mole of electron, it will deposit only 1 mole of product. Okay, 1 mole of electron, that is 1 Faraday. 1 Faraday will give you 1 mole of product with where the it requires only one mole of electron to get reduced. So for the following equation, please try to solve the equation. It is very simple. It is based on Faraday's first law, that is the amount of electrolyte deposited is directly proportional to the amount of charge passed through the solution. So the question says a solution of nickel nitrate is electrolyzed between platinum electrodes using current of 5 ampere for 20 minutes. What mass of nickel is deposited at the cathode? So weight, we just understood that the weight is directly proportional to the charge or current passed. So weight is equal to I into T. Current passed for the time interval. So as we know that weight is equal to I into T. Here the current pass is 5 amperes for time period of 20 minutes, but we'll consider in seconds. So 20 into 60 seconds. Therefore we have a charge of the charge. This is the charge. Charge is 6000 ampere into seconds will give you coulomb charge. COLOUMB coulomb charge. So in order to convert nickel 2 plus 2 electrons into nickel, the how many mole of electrons are required to convert into 1 mole? 1 mole of nickel requires 2 mole of electrons, that is 2 into 96500 coulomb are required to convert 1 mole. 1 mole, and 1 mole has a mass of 58.7. So 2 into 96500, that is 193,000 coulomb are required. 193,000 coulomb are required to convert 58.7 gram. Okay, in order to deposit 58.7 gram, you require 193,000. So 1 coulomb will deposit 58.7 divided by 193,000, and since we calculated 6,000, over here 6,000 will give you 58.7 divided by 193,000 into 6,000. So calculate the value, how much it will be. It will be 1.812 gram of nickel will be deposited. Okay, here what point was to be noted, that in order to deposit 1 mole of nickel, you require 2 mole of electrons. So 2 mole of electrons, that is 2 mole of electrons has a charge of 2 Faraday. 2 Faradays will deposit 1 mole. 1 mole has a mass of 58.7. So from here you can just calculated the charge, that is how much this charge could deposit, we just calculated. So coming to the next question, how long will it take to deposit 0.2 gram of silver when silver nitrate solution is electrolyzed using 0.5 ampere of current? This is similar to the previous one. As we know that silver, in order to deposit, it require 1 mole of electron to deposit 1 mole of silver ion. Okay, that is 96500 coulomb charge is required to deposit 108 gram of silver. So they just said that we need to calculate charge. Charge is equal to current into time. So we just understood from the equation that 108 gram requires 96500 charge. 1 gram will require 96500 charge by 108 coulomb charge, and 0.2 gram will require 96500 divided by 108 into 0.2. So solving this, we'll get the amount charge, that is 178.7 coulomb is required. So for 178.7 coulomb with zero point 0.5 ampere, how much time will be required? So time equal to current by charge by current. Charge is 178.7 divided by zero point 0.5 ampere. You will get time, that is 357.4 seconds. Okay. Now coming to the products of electrolysis. The products of electrolysis depends upon the nature of the electrolyte. The product of the electrolysis depends the nature of depends upon the nature of the electrolyte being electrolyzed, the nature of the and the nature of electrodes. If the electrode is like platinum or gold, they do not take part in a chemical reaction, that is, they neither lose or gain electrons. If the electrodes are reactive, then they will take part in the chemical reaction and the products will be different as compared to the inert electrode. So generally we prefer that we use inert electrodes like platinum and gold only, as they do not take part in the chemical reaction. And the other thing that we keep in mind is the electrode potential of oxidizing and reducing species. Some of the electrochemical chemical processes although feasible but slow in their rates at lower voltage. Excuse me. These require extra voltage and over voltage at which these processes will take place. The product of the electrolysis also differ in molten state and aqueous solution of the electrolyte. So now we'll discuss some types of cell. Talking about the primary cells. A primary cell is the one in which electrical energy is produced by the chemical reaction, or we can say it as a galvanic cell. Okay, here chemical energy is converting into electrical energy, and the charge is used only once, cannot be recharged. The batteries that you use in watch or these toys and everything, the cell batteries that we use in remotes and everything containing kind of uh, uh, this kind of appearance, these are basically primary cells. These cannot be recharged, these are used for only once. Example are Daniel cell, dry cell, or mercury cell. So what is the reaction happening in these cells? Dry cell, at anode we have zinc. Zinc gets converted into zinc 2 positive ions and release 2 electrons. And in cathode we have manganese oxide along with the ammonium ions. And those manganese oxide and ammonium ions undergo reduction and convert into manganese oxohydroxide along with the ammonia. The net reaction is zinc with ammonium ions in presence of manganese oxide is converted into zinc ions, oxohydroxo along with the release of ammonia gas. Similarly, the mercury cell, the mercury cell is also a primary cell that cannot be recharged. In the mercury cell, you see the zinc at the anode along with the 2OH minus ions. In the presence of 2OH minus ions, zinc gets converted into zinc oxide. H2O and 2 electrons are the side products. Whereas at cathode, this mercury oxide is present, that in the presence of H2O and those 2 electrons is converted into liquid mercury along with the release of 2H minus ion. So the net reaction is zinc plus mercury oxide will give you zinc oxide plus mercury liquid. Now coming to the secondary cells. Secondary cells are those which are used for storing electricity, like lead storage battery, nickel cadmium cell, etc. Lead storage battery is the one that we use in inverters. Okay, this is used in our ohms. So these could be recharged. That means the reactions are reversible. If you provide electricity, it will go reverse, and if you don't want to take electricity out of this, they will go spontaneously and produce electricity for you. Lead storage battery contains lead sulfate at the anode, where lead along with the sulfate ions makes lead sulfate along with the release of two electrons. At cathode, the lead oxide along with the sulfate ions and 4H plus and 2 electrons gives lead sulfate and 2H2O molecules. The overall reaction could be said as lead plus lead oxide in the presence of 2H2SO4 gives two lead sulfate molecules along with the release of 2H2O liquid. On recharging the battery, the cell is reversed. The reaction is reversed. Similarly, in the case of nickel cadmium cell, it is another type of secondary cell which has stronger lifetime than the lead storage cell, but most expensive to manufacture. The overall reaction includes the cadmium along with the nickel hydroxide gives cadmium oxide with two nickel hydroxide molecule and one H2O molecule. Coming to the fuel cells, the fuel cells are basically you that use this hydrogen and oxygen gas. So it has basically two compartments. The structure is somewhat like this. uh, there is an electrolyte in between, so from here H2 enters, from here O2 enters. Okay. So at anode, H2O along with the 4 hydroxide ion, the hydroxide ion present in between electrolyte. So OH minus will give you 4 H2O molecules and 4 electrons. At cathode, O2 is coming from at cathode. O2 along with the 2 H2O molecules plus 4 electrons will give you 4 OH minus ions. So overall reaction is that 2 H2O plus O2 will give you 2 H2O molecule. This is a green fuels. It follows the green chemistry. Basically, there are no mm, harmful side products. Such cells are used in the rocket fuels and everything because they do not produce any harmful uh, product with them. And now we'll talk about the term corrosion. We know that if we place iron in the atmosphere, there will be iron is basically a shiny has a shiny surface. Okay, shiny metallic surface. If you place in it atmosphere containing O2 and H2O, what will happen? Rust will start developing, brown colored rust. What is this brown colored rust? This is because of the formation of iron, uh, the corrosion of iron, that is, or we can say corrosion of iron, or we can call it as rusting. So iron gets oxidized to the iron 2 plus jade along with the release of two electrons, and the reduction is happening because of the oxygen. This oxygen is getting reduced to the 2H2O molecules along with the taking 4 electrons and 4H plus ions. Now we'll talk about the term galvanization. Galvanization is the process of coating zinc over iron so as to protect it from rusting. So since iron gets rusted over time in the presence of oxygen, so what we'll do, we'll protect the this iron piece by galvanizing zinc over it, a layer of zinc over it. We can do it by taking this iron as cathode and providing a solution of zinc in the electrolyte. So what will happen on electrolysis? On cathode, reduction happens. The zinc 2 positive ions will start depositing over the iron surface, and that's how the galvanization will work. Okay, coming to the cathodic production. In Instead of coating more reactive metal on iron, the use of such metal is made as sacrificial anode. This is all for the today's part. We'll discuss some more content in the next video. Thanks for watching.